Hi, everyone. So what kind of a matrix acts like 1? Well, we talked about a zero matrix before, something with all zeros in it, right? But what matrix acts like a 1? Well, this may not be obvious to you, but it's this over here. A matrix with 1s along the main diagonal and 0s everywhere else. And what form is this matrix in? It's a really great example of what kind of a form. Not just row echelon form, but reduced row echelon form, RRE. Leading 1s all over here on the diagonal, 0s everywhere else. So for example, I sub 3 is the 3 by 3 identity, 1s along the main diagonal, 0s everywhere else. In general, I sub n is the n by n identity. These matrices are multiplicative identities, just as the 0 matrix here was an additive identity for 2 by 3 matrices. These matrices here are multiplicative identities in that they play the role of 1, in the sense that when you multiply by 1, you get the original thing back. In this case, if you multiply this matrix by any compatible matrix on one side or the other, meaning that the matrix sizes work out when you do products, then you're going to get the other guy. So in that sense, it acts like 1. Multiply by this, you preserve the other guy. Just like 1 times 3 is 3. Play with it, see why that is. If A is an n by n matrix, then A times the n by n identity is A, you get A back, and also in reverse. We do have commutativity. Square matrices commute with their corresponding identity matrices. 3 by 3 matrices will always commute with these, meaning that the order doesn't matter when you take products. Again, although matrix multiplication is not in general commutative, it is true that the identity matrix commutes with a matrix of the same size. And in fact, even if you have a non-square matrix, like over here, as long as you have compatibility, you'll get this guy back. Okay, now, where can matrix notation help us in terms of solving systems of linear equations? Let's say we want to solve this system. And I know it might be a bit disorienting because we don't see x, y, and z. We see x sub 1, x sub 2, and x sub 3. A system of 3 linear equations in 3 unknowns. Now, believe it or not, we can write this system in a matrix vector form. AX, sometimes x is written like this, like the way we used to write vectors. AX equals B, another vector. AX equals B. Or you can think of these all as matrices or as a combination of matrices and vectors. A times the vector x equals the vector b. Now, if you don't see why that is, remember that old trick, if you raise this thing up, or you don't even have to do that. For example, how do we get that first equation? Imagine taking the dot product of this and this. 1 times x1 plus 1 times x2 minus 3 times x3, that's the left-hand side here, equals 9. And so forth. From the second row, and these variables equals 6, we get that. Over here, x1 minus x2 plus x3 equals negative 5. So this is really convenient. It works out. And this is, incidentally, the coefficient matrix. See, if you had done the augmented matrix, A slash B, if you had done the augmented matrix, hey, coefficient matrix goes here, right-hand side goes here. All right. Now, what if we perform Gauss-Jordan elimination to A slash B? Again, it might be using this vector notation. So Gauss-Jordan, that means that we have to take this thing to reduced row echelon form. REF, reduced row echelon form. We want to go to that. And it's unique. Remember, each matrix has only one unique reduced row echelon form. Okay, so again, we're setting up this augmented matrix the way we used to, way back in section 8.1, right? If you had done, right, basically the way you did this old school in 8.1, this thing here, I'm writing over here, A/B. Our old school augmented matrix from 8.1. Haven't seen him in a while. Now, if you take this to row echelon form, you get that. So if you're doing GEBS, you can go to here and then write the system and back substitute, right? It's an upper triangular system and back substitute. That's for GEBS. You could solve a system that way, assuming there's a unique solution. And there is here because, see here, if you have, we have this in that old school row echelon form. But I said go to Gauss-Jordan. If you go to Gauss-Jordan and you eliminate up, they end up with this. Now again, on the final, I will not require you to use Gauss-Jordan, but take a look here. Interesting. So on the left side, who is that? Who is that? I sound like I own a pet. This is I sub 3. It's the 3 by 3 identity. And guess what comes over here? Well, what happens, right? If you work this out, right? The unknowns were x sub 1, x sub 2, x sub 3. I'll write that. X sub 1, x sub 2, x sub 3. X sub 1 equals 0. X sub 2 equals 3. X sub 3 equals negative 2. All right. Well, hey, looky here. We get the coordinates of our solution. You know what this is? This is x. It's our solution for x. It's a solution vector. It's x as a solution vector. Pops up over here. We mentioned this before with Gauss-Jordan, that if you can get it into this great a form, you can read off coordinates just on the right-hand side. Instead of using braces, I'll express this vector as just a column vector, 0, 3, negative 2. Okay, it's assumed that we know that this is x sub 1, the value for x sub 2 here, value for x sub 3 here. And you can check. All right, so what is Gauss-Jordan? I talked and rambled on about Gauss-Jordan. We start with this, the old school first augmented matrix from 8.1. What's Gauss-Jordan? You go from here to here. Pretty cool. Assuming that you have one unique solution. You can only possibly get the identity matrix there if there is one unique solution, assuming it's a square system. Otherwise, it's impossible to get that. All right. So at the end here, I was basically connecting matrix notation and solving systems. So next time, well, what are some other ways of looking at this? We have AX equals B. Could we solve for X? In a way, yeah, just from this formula. Next time, inverse matrices.